Hello everyone, this is Himabindu, Assistant Professor in IARE College. So today in this video I would like to explain about the grammars. So what are the grammars in theory of computation? So how many grammars are there and what are the types of grammars we have in the theory of computation we will discuss in this video. So, introduction to the grammar. So, how we need to define this grammar? So, grammar is nothing but a systematic set of rules. So, set of rules we are representing in a systematic way is named as a grammars. And standard way of representing the language. So, the language what we are till now discussing. So, the language which is a regular language or context-free language, whatever it is, the language which we need to systematically represent that in a grammar. So grammar is nothing but like English, what we have as a grammar. Here, this theory of computation is also having some grammar. So how many types of grammars we have, we will discuss. And here, what is meant by grammar? Grammar is a finite set of formal rules. So it is a set of formal rules for generating systematically correct sentences. So here we need to represent the language in a correct sentences or meaningful correct sentences. So here, so what is meant by grammar? A syntactically correct sentences. So here the language which we are which we are representing in a systematic way is named as a grammar. And the constitute of grammar. So what is meant by constitute of grammar? In the theory of computation, so grammar is having the two basic elements. So what are those in the sense? One is a terminal and second one is the non-terminal. So terminals and non-terminals, both are the two important elements for the grammar. So and terminal symbols. So a terminal symbol are those which are the components of sentences generated using a grammar or represented as using a small letters. So here the grammar is having the two elements. First one is the terminal and second one is the non-terminal. So the terminal which is represented with the small letters. So generally we'll represent the terminals which are equivalent to the sigma. So sigma which is having the input values like 0, 1 or a, b. So all are representing with the small letters. So the terminals which are represented with the small letters, and with these terminal symbols only we are going to form the strings. Strings are words. Suppose here this language which is having the terminals a comma b. So with this a comma b terminals we can form the strings like AAB and BAA. Like this we can form the strings. So here these strings which are belongs to the language. So the language which is represented in a systematically way, and this is represented as a grammar, and this grammar is having the two basic elements. One is the terminal and the second one is the non-terminal. So terminal which is represented with the small letters, and coming to the non-terminal symbols are those symbols which take part in generation of sentence. So but are not correspond component of the sentences. So here we already discussed the language which is having the elements which are having the terminals a comma b. So with this a comma b terminals only we can form the strings. So here if suppose we'll take the language. So the language L1 says that starts with 0 and end with 1. So this says that this language says that it is a set of strings we need to form with this language, and the sigma is equal to 0, 1. And with this state, with this language, we will form the language strings like this. So starts with 0 and ends with 1. So in between anything we can represent. So why? Because we are having the two input values. In between there is a condition, not only 0, not only 1, whatever it is, we need to make a choice of these two options. So here I will write this is the minimum, and if I kept one middle, and it is going to be like this, and 0 0, if I am keeping the 0 as a middle part, like this we can form the strings. So in this language of strings, so only we have the terminal symbols. So the non-terminal symbols are not a part of sentence. So here what we are going to generate the sentences, those are only for generation of sentences, and but it is not a component of the string. So what we are going to perform on the strings, finally we are getting the strings, those strings based on the non-terminal values, but it is not a part in the sentences. And non-terminal symbols are also called as auxiliary symbols and words and variables. So here these symbols are represented using the capital letters. So generally this grammar is having the two things. One is a terminal and non-terminal. So terminals are represented with the small letters and non-terminals are represented with the capital letters. So these are the two elements which are basics of grammar. So grammar which is having the two elements, one is the terminal symbol and second one is the non-terminal symbol. So terminal symbols are small letter represented with the small letters, and non-terminal symbols are represented with the capital letters. And here what is the definition of the grammar? So this is all about the grammar, which is the general abbreviation, in general thing which we are going to discuss in the theory of computation. In theory of computation, we have languages. So formal languages we have. So for every language there is one grammar. So in generalized way we are representing this grammar. So here, coming to the for not only a particular language, we are all over languages. How many languages are there in the theory of computation? So for all the languages, we are generalizing this grammar. And here, what is the definition of grammar? So here, in this definition, we have a four tuple notation. The grammar which is having the four tuple notation. The one is N, T and P, S. So this N and T we already discussed. So what is this N and T? So the grammar which is having the two basic elements. So two basic elements. So what are those two basic elements? One is terminal and second one is non-terminal. So these are the two important elements for the grammar. And here coming to the definition of grammar, so these two elements are there. Along with that one, two more tuples, that is P for production and S for status symbol. So this four tuple notation, so N is represented as a finite non-empty set of non-terminal symbols, and T is represented as a finite set of terminal symbols, and P is a non-empty set of production rules, and S is a start symbol, the symbol from where we start the production. We start the production of producing our sentences or strings. So here we will represent it with the strings. Mainly we will represent with the strings, the language which is having the strings. So this one, and this is about the definition. So in the definition, it is having the four tuple notation. So first one is the non-terminal symbols, and second one is the terminal symbols, and P for production rule and S for start symbol. And coming to the production rules. So here we now discussed the terminals and non-terminals in the previous slide, and now we will discuss about the production rules. So the production rule or production rule in a computer science is a rewrite rule. So here it is a rewrite rule specifying a symbol substitution. So here we need to substitute, so we need to form the equations. And if suppose here s tends to a b is there, so whenever s is appear, we can write this ab value. So this is mean by substitution. So this is the computer science is a rewrite rule specifying the symbol substitution that can be recursively performed. So this is only not only for one string we are performing, we can apply this entire equation to the all over the strings. So all over strings which are belongs to the same language. So this is a recursively we can produce the recursively performed to generate a new symbol sequences. So here, so this sequences which we are only not only for only one string or one language. So this sequence of steps, what we are having as a production rule, we can use or substitute the values in the strings, and it is of the form alpha tends to beta. So here alpha tends to beta and nothing but here left hand side and right hand side we have. Based on the grammar, so here different types of grammars. So these conditions, these limitations are differing here. So grammar generally we have a grammar representation alpha, this is alpha and tends to beta. So alpha value is different and beta value is different here. So it is a alpha based on the grammar. So how many types of grammars we have? So for every grammar there is a conditions like alpha is like that, the length of the alpha should be like this only, and the length of beta should be like this only, and it's the combination of terminals and non-terminals. Like that there are conditions. So here we will discuss about the grammars. And these are the examples. So here example, we'll take one example. So in this one it is represented with the 4 tuple notation. So 4 tuple notation T. So T is nothing but terminal symbols. In this one terminal symbols we are representing with the AB, and P for production. So here the productions are A tends to A, capital A, small a, and again A tends to A, B, and A tends to A, and A tends to B, and A tends to epsilon. So here all together we will write it as A tends to capital A, small a, and A, B, and A and B and epsilon. So this is the production rule what we have. And here in this one we have the terminal symbols like terminal A, B. So and here S is the starting state. So S here in this place only we have one production rule. So in this one A is the starting state. So we can represent it with the S. And T is the terminal symbols and a set of terminal symbols. So here we can production rules A. S is equal to E, start symbol. So here this is about the example of the general grammar. So generally we have a limitation. So here left hand side we have a right hand side. So left hand side this many terminals and non-terminals should be there, and this many terminals and non-terminals should be there in the right hand side. So these are the condition based on the grammars what we are selecting. And how many types of different types of grammars. So we just discussed. So these two slides are only generalized specification about the grammar. So general representation of a grammar. And here, from here we can discuss about the types of grammars, and based on the grammar what we are selecting, we have the production rules differ here. And different types of grammars. So grammar can be divided in on basis of types of production rules. So here types of grammars will be divided into a types of production rules. So as now just discussed it. So here this kind of production rules. So left hand side only single length, and here it is a combination of terminal and non-terminal combination. This is one type. And if you take the second type, so left hand side there is no condition like A like this, and A terminal. This is one condition. And so it is a combination of, so A and like this, and A, and there is a one combination of left hand side, the length of the left hand side and right hand side condition. So like this. So these are the different types of production rules we have. So based on this different types, we can divide this grammar. So this we can divide this grammar so based on the production rules. So production rules we have a different types in the sense type 0, type 1 and type 2 and type 3. So these type 0, type 1, type 2, type 3 we already discussed in the Chomsky hierarchy of previous video. So let me briefly discuss about this one. So here if you take a type, so type 3 is a subset of, type 3 is a subset of type 1, type 2, and type 2 is a subset of type 1, and type 1 is a subset of type 0. So these are the types of grammar. So this grammar is generally we will write type 0 as a unrestricted grammar. Restricted grammar. Unrestricted grammar. And type 1 is a context sensitive grammar. Context sensitive grammar. And type 2 is a context free grammar. And type 3 is a regular grammar. So here based on the production rules, to different types of, based on the types of production rules, we can divide the grammar into a four parts. So four types. So one is type 0 and type 1 and type 2, type 3. So these grammars we already, these types of grammars we already discussed in the Chomsky hierarchy. Just briefly I discussed about this type 0, type 1 and type 2 grammars we will discuss in the coming slides. So here, and this is about the types of production rules, and the second one is number of derivation trees. So derivation trees we already discussed in the second unit, a regular grammar which is having the derivation tree. So regular left linear derivation, right linear derivation, leftmost derivation tree, rightmost derivation tree. So these are all the derivations which based on the derivations also we can divide the grammar. So here second type is on the basis of number of derivation trees. So number of derivation trees are also we have the ambiguous grammar, unambiguous grammar. So ambiguous grammar is nothing but if you write for the same production rule, so for this grammar we can represent. So this two different ways we can represent the two derivations for the one grammar. So that is represented as ambiguous grammar, and unambiguous is for one grammar we can represent with the one derivation tree. Like that we have a derivation tree. So derivation, based on the derivation tree we can divide the types of grammars, and this is one type. And third one is on the basis of number of strings. So number of strings, how many number of strings we have. So based on the number of strings, so number of strings, the here left hand side, right hand side, the length which we are going to specifically choose from the alpha tends to beta. So this is also one different type. So one is a number of, so first based on the production rules, and second one is the derivation tree and based on the number of strings. So number of strings also recursive grammar, non-recursive. That is nothing but a restricted and unrestricted grammar. So these are the different types of grammars we have. in the theory of computation. And coming to the type 3, so which we discussed, so this is the type 3 is the regular grammar. So regular grammar, what are the regular grammar rules and how to convert this into a finite automata, I will see. And type 3 grammar, so it is named as a regular grammar. So this regular grammar generates the regular languages. So here what we will, this grammar generates the regular languages. They have a single non-terminal on the left hand side and right hand side consisting of a single terminal, or it is a combination of terminal or non-terminal. So here coming to the production, so grammar which is general representation, V or VSTP. So V is nothing but non-terminal and start symbol and T for a terminal and P for production. So for a regular grammar also, the definition of the regular grammar is also for tuple and in this one, this production rule which is having the, so we discussed based on the production rule, the type of grammar is divided. So that is a type 0 or type 1, type 2, type 3. In this one, type 3 we are going to take. In this one, type 3 production rules, how it is going to be changed from the type 2 grammar. And the production rules, coming to the production rules, so here A tends to XB and A tends to X and A tends to BX. So here, so with this statement says that left hand side, so this left hand side, it is only having the single non-terminal value. So capital A are represented with the non-terminals and small letters are represented with the terminals. So here let me write this by seeing this example, or we'll see what are the V is equal to, non-terminals are A comma B and terminals are X. V is nothing but a non-terminals and X is equal, terminal is equal to X. So here by seeing this one, so left hand side of every production, it is having only a single, the length of the left hand side is equal to only 1. So 1, that is also non-terminal. So that is also non-terminal. So non-terminal. And right hand side, it is a combination of V union T. So V union T or only T. So these are the possibilities of the production rules for the type 3 grammar. And where V, A comma B are the variables and which X belongs to the T star. T star is nothing but terminal. So how many times we can repeat the value of X. And the different types of grammars for the regular grammar. So regular grammars are having the two types. One is a left linear grammar and right linear grammar. So left linear grammar and right linear grammar. So left linear grammar, the productions are of the form in the productions. If all the productions are of the form A tends to Bx. So here, if you observe this production rules of left hand side and right hand side, left linear grammar and right linear grammar. So this production rules, left linear represent the non-terminal is in the left hand side. So this production rule having the limitation, the left hand side it is a single and that is also non-terminal value. But here this right hand side there is no restriction. So right hand side, so this right hand side, whenever we'll take right hand side, the left hand, so left part is having the non-terminal, so non-terminal value and followed by the terminal. So this is a left linear grammar. And say at the same time, So we will discuss this right hand side. So terminal followed by the right hand side. So this is a right linear grammar. So here right hand side. So right hand side of the production rule. So this we are talking. So this right hand side of the production rule, whenever it is having the terminal, non-terminal with the right side of the right side of the production rule, right hand side of the production rule, it is a right linear grammar. So this is about the left linear grammar and right linear grammar. The language generated by the type 3 grammar is a regular grammar, and for finite automata can be designed, and finite automata can be converted into a type 3 grammar. So here we are discussing about the regular grammar. So this regular grammar will generate the regular languages, and with the regular languages we can also convert that to a finite automata. So in finite automata we have a types of finite automata. In that one we will form into a one finite automata. We'll take one grammar and we'll convert it to a NFA or DFA or epsilon NFA we can convert. And here how to convert the given grammar into a finite automata. So generally we have to equalize these two values. Generally grammar is represented with a 4 tuple, and finite automata is represented with a 5 tuple. Q and sigma and delta and Q not initial state and final state. So we need to equalize these two. So how to equalize this one in the sense? So the capital Q is a finite set of states that is equivalent to V, and sigma which is equivalent to the T. So sigma is equal to T, and delta is nothing but, so delta is equal to production rules, and here for initial state which is equivalent to S, and final state based on the production rules we will decide. So here these are all we need to equalize this one. Then we will follow the algorithm, like we have to start with the process starts with the start state. So here we need to start with the start state, repeat the process for each state. So each state we need to repeat the process. Write the production as of the output followed by the state on which the transition is going. So output followed by the state, which the transition is going. And last add epsilon to end the derivation. So here we need to add the epsilon to end the derivation. And we will discuss this algorithm with the example. So here is the example we have taken. So here we have the input as a finite automata, and we need to convert it to a regular grammar. How we will see. So first one we need to start with the start state. So start state is here A. So here A I need to. So and coming to the rule. So rule it is having the terminal. Non-terminal left hand side only a single non-terminal should be there. So that's why initial state I am taking as a, and here, and let me equalize this two first thing. So here we have a finite automata. So Q is equal to here A comma B, and sigma is equal to A comma B, and like this. And here we need to equalize this one. So with the V and T. So V is equal to A T, A B, T is equal to small letters A B. And here A tends to, so here the self loop it is having A value. So here what the algorithm says, the A from A state, if you give A as an input, it will reaching the same state. So what it says, this state. So this is the present state and this is the next state. So and also we have one more element B input also. So A tends to B, and it is for B input, it is reaching the A value, A state only. And if you give A as a state, it is reaching the B state, capital B state. And we finish the state inputs. So here, so by seeing this diagram, we can say that it is a NFA. How we can say that it is NFA? So for the A input, so for the same input, it is going to reach the two states. So A, if you take A as an input, it is reaching the two states. So that we can say that by seeing it is a NFE, non-deterministic finite automata. And now we finish the A state and we will take the B state. So B tends to, if you give A as an input from the B state, it is reaching the same state only. And if you give B as an input, it is reaching the same state. And so algorithm for last step is we need to add the derivative. We need to add the epsilon symbol. So epsilon symbol for the input to end the derivation. And here we need to write, so A tends to capital A and B and AB. And also we have the value A tends to AB and B, and we need to add the epsilon symbol. So this is the grammar what we got from the finite automata. So this is about the grammar which we are going to, if we are given as a finite automata, we need to convert it to a grammar. In the sense, we need to follow this algorithm. And this is about the regular grammar. And next one is about the type 2 grammar, that is a context-free grammar. So type 2 grammar is a context-free grammar. So this language is generated by the context-free grammar, is accepted by the pushdown automata. So it is a subset of type 0 and type 1. So it is a subset of type 0 and type 1. See this type 3 is a subset of type 2, like this, and this is a type 1 and type 0 comma type 1, it is a subset of type 2. So here the type 1 and the superset of type 3 grammar too. So it is a superset of type 3 grammar, and also called as phrase structured grammar. So it is also named as a phrase structured grammar. And the different context-free grammars can generate the same context-free language. So here, if you take the different context-free grammars, can generate the same context-free language. And the classification of context-free grammar is done on the basis of number of past trees. So here, how many previous regular grammar, it is having the derivation tree, and here number of right hand side derivation and left hand side derivation. Like that, here also we have the past trees and different types of grammars for the context free grammar based on the past trees. So only one past tree is there, we can say that it is a unambiguous. So for only one, more than one past tree is available for the same grammar, we can say that it is a ambiguous grammar. And coming to the production rules, so A tends to B, that is alpha tends to beta. So A belongs to the non-terminal, that is A is a non-terminal, and B is a terminal. So there is any string which is formed with the sigma symbols. And this is an example. So here also right and left hand side we have a single value, and here right hand side not only a terminals, we can also have the non-terminals. Two non-terminals should be there and a single non-terminal should be there, and it is only a terminal value also there. So these are all the production rules for the context-free grammar. And we'll take the one context-free grammar and we will convert it to a pushdown automata. So how to take this is the context free grammar, and we need to convert it to a push down automata. So what are the steps we need to follow for this one? So here the transition. So our input is in the production rule. So we need to convert it to a delta. So that is the delta is nothing but transition function. So by seeing by seeing this production rules, we can form the transition functions. How we will see. So we already know that this push down automata, which is having the stack representation. So we need to push the element into the stack, and we need to pop elements into the stack. Based on that only, we need to perform the transition function. So in this one, initially we initialize with the stack is going to be initialized with the z naught. Like that, we need to we already discussed this push down automata construction in the previous videos, and now we will convert this grammar into a push down automata. So this push down automata needs the transition function. So what this transition function? So this is represented with the ID. Instantaneous transition functions of the push down automata is defined with the IDs. That is nothing but instantaneous description. So it is having the three tuple. So what is the three tuple in the sense? Delta of Q is the initial state, and here initializing the value and on top of the stack symbol, and top of the stack symbol is S, and which leads to the next state. This is the current state, and this is the next state, and with the value. So for the substitution, we will get the value. So it's like this. So here from this for this non-terminal value, we need to substitute the value. So when we have as a input here, what we are going to place, replace or substitute the value with this one. So this is the IDs. So if you have the multiple IDs, we can write all the moves in the turnstile notation. So let me write this transition function. So here we have the conditions, two conditions so whatever there. So q comma epsilon, and if you say this is alpha, and we can say that it is a beta. So alpha we need to represent with the delta of turnstile notation, delta of next state comma beta, like this. This is one rule. And if you have how many values are there, how many terminals are there, so we need to write for all the terminals, like we need to match the terminals. So here I am taking as a terminal and terminal there, and we need to follow the transition like delta of transition of q comma epsilon. We need to pop the value. So whenever these two rules we need to follow for the construction of push down automata from the context free grammar. So by observing these two rules, we can form the grammar. We can form the transition functions here. So here delta of current state is q, and here we'll assume this only one state it is having. So here one state. So why? Because we have only the value, the non-terminal is equal to only we have S. Assume that we have only one value it is having, that is a Q, and initially the stack is empty. So empty, and top of the stack symbol is we are going to start with the S state, and when we replace this one, we will get the value. We will get the value transition of q comma s is substituted with the beta. So beta is equal to ASB, and this is for first production rule, and we will write the production rule 2. So individually we will write epsilon comma s is equal to, so we have three choices: s tends to A, s tends to B, and s tends to epsilon. So here we will write it as a delta of q comma A and slash delta of q comma B and slash q comma delta of q comma epsilon. and we need to write the terminal, second rule. So this is all for the first rule we followed, and for every production rule we have written for the substitution, the production rule like this. And then we need to follow this second rule. So what it says that how many terminals are there in the production. So we need to write all the productions in this form. So delta of Q comma Q comma, how many terminals? So small letters are all terminals. So here T is equal to A comma B comma epsilon also. So A comma B epsilon. So epsilon comma epsilon, sorry, A comma A tends to delta of Q comma epsilon. And this is for A input and B input, delta of Q comma epsilon. And for epsilon also, we need to write epsilon. So this is all the transition functions, and these transition functions will help in the derivation, stimulating the string. So if you take one string from this grammar, and we will stimulate these strings with the finally if you are ending with the empty stack, we can say that the string is going to be accepted like that. And this is about the conversion of context free grammar to a push down automata. And here, what are the differences between the context free grammar and regular grammar? So we have some points, and based on the parameters, we have the differences between the two grammars. One is a recognizer. So if you take the parameter as a recognizer, so context free grammar, it is having the push down automata, and the regular grammar, it is having the finite automata. And coming to the rules parameter, so rules are nothing but predictions. Based on the predictions only, the rules are going to be happen. So here the rules, so coming to the rules, A tends to beta. So this is about the context free grammar. So left hand side always only one single non-terminal, and right hand side it is a combination of A or B. So the production rules are B. So B tends to any string. So not only a single string, we can also form with the non-terminal symbol. And here also the V is nothing but non-terminal, which is followed by the terminal or only single terminal. So we have two different types of grammars. One is left linear grammar and right linear grammar. And the restrictions. So coming to the restrictions, less than regular grammar. So restrictions are compared with the regular grammar, the restrictions are less in the context free grammar. And coming to the context free grammar comparison, the regular grammars are having the more restrictions. So the right hand side of production has no restrictions. So right hand side there is no restriction. So we can have the multiple combinations of terminal and non-terminal. So here it is in right hand side the production should be either left linear or right linear. So only we need to follow these two things. And the intersection. So intersection of two context-free grammars, to context-free to CFL, context-free language need not be a context-free language. But here in the context-free grammar, in the regular grammar, the two intersection of two regular grammars is a regular grammar only. And the complement, coming to the complement, they are not closed under the complement. So context-free grammars are not closed under the grammar, not closed under the complement, and here closed under the complement. And range, the range of the regular languages, context free languages come under the CFG is wide. So here the range is wide when compared to the regular grammar, and the range of languages thus comes under the regular grammar is less than CFG. And here the example, so we already discussed. So S tends to AB and terminals only single terminals, and here this right hand side, either left linear or right linear grammar should be there. So these are all about the differences between the regular grammar and context free grammar. And context sensitive grammar. Till now we have discussed about the type 3 and type 2. So that is nothing but, so type 3 is a regular grammar and type 2 is a context free grammar. And now type 1 we will discuss. So what is nothing but, it is a context sensitive grammar. So context sensitive grammar may have more than one symbol at the left hand side of the production of their production rule. So in these two grammars we observe the left hand side. So the left hand side of production rule is equal, length is equal to only one, that is also a non-terminal. But coming to the context sensitive grammar, it is the left hand side of the not only limited to the one, it is also with the multiple combination, and the length is the length of left hand and right hand is different here, and the number of symbols on the left hand side must not exceed the number of symbols on the right hand side. So with this statement we can say that length, if suppose so A, B is there and which leads to the production rule, so this A, B. So the length of left hand side is 2 and right hand side is 3. So this condition is satisfied here. So this condition is satisfied, so that we can say that it is a context sensitive language. Whenever we have the length is 3 here and length of the right hand side is 2, so we can't say that it is a context sensitive grammar. Why? Because it comes under the type 0. So there is no restriction. We will discuss that later. So the length of the left hand side is not exceeding the right hand side of the length. So that is the point we need to note in the context sensitive grammar. And the rule of the form, so A tends to epsilon is not allowed unless A is a start symbol. So whenever the A is only the start symbol, suppose here, so here in this one we can allow the epsilon symbol. In these cases we can't allow this epsilon symbol. So this is the point we need to note in the context sensitive grammar. It does not occur on the right hand side of any rule. So here only for start symbol only we need to allow this epsilon symbol. And type 1 grammar has to be in type 0, and the type 1 production should be in the form of V tends to T. So non-terminal tends to T also allowed here. The count symbol in the V is less than or equal to T. The count symbol, just now we discussed the count symbol in the V. So count symbol in V is less than or equal to T. So this is the thing we need to less than or equal to T. So this is the thing we already discussed. So the length of the left hand side is less than or equal to right hand side of the production rule. And this is the example we need to we have for the context sensitive grammar. And if you observe the first production, it is having this condition is satisfying. The length is 1 here and length is 2 here in the right hand side. And here also we have a combination of terminals and non-terminal combinations. And here the right hand side, left hand side, it is having the length 2 and right hand side it is having the length 3. So this is also satisfied. And here only a single terminal also for allowed. So that is B tends to capital small b. So this is the example of context sensitive grammar. And coming to the context unrestricted grammar, so that is named as a type 0 grammar. So the type 0 grammar generates recursively enumerable. So we can generate the recursively enumerable languages. That is nothing but a type 0, that is nothing but unrestricted grammar we can write. So in type 0, the production has no restrictions. So here, till now, in three types of grammars, we saw the limitations, or we saw the restrictions in the grammar. So left hand side only this many length, and right hand side this length, and left hand side only single length, and right hand side it is having the multiple values with the combination of terminals and non-terminals, like that we have. But here there is no restrictions kind of thing. So the length of left hand, right hand equal or greater than, less than, whatever it is, we are going to be allowed in the type 0 grammar. So that's why it is named as a unrestricted grammar. And there may be any phase structure grammar which includes all formal grammars. So any phase structure grammar which includes all formal grammars we can represent in the single grammar only. So they generate the language which is recognized by the Turing machine. So here this Turing machine, unrestricted grammar which is used to recognize the Turing machine. The production can be of the form A tends to B. So that is where a string of terminals and terminals with at least one non-terminal symbols, and A cannot be null. So here A cannot be null, and B is a string of terminals and non-terminals. So here instead of this A tends to alpha tends to beta, we will write. So A is which is not cannot be null. So the alpha cannot be null. So null is nothing but that is a pi. So beta is nothing but the string which is a terminal and non-terminal. So B is nothing but terminal and non-terminal. So this is the example. So here S tends to A, and length is here, right hand side is 4, and here also 2 and 3. So and here 2 equalize, and 2 equalize. So the like this we have a no restriction in the production rules. So production rules we don't have any restrictions in the type 0 grammar. So and these are the references. And coming to the let me briefly write types, how many types of grammars we have. So types of grammars we have with 4 types based on the production rules. And production rules, so in regular grammars there is no restriction. We have only 2 types. Right hand side we have either it is left linear grammar or right linear grammar. And in the context free grammar, right hand side it is having the terminal non-terminal combination. And in the context sensitive grammar, the length is the left hand side of the length, and the right hand side is greater than or equal to, less than or equal to right hand side. So this is in the context sensitive grammar. And coming to the unrestricted grammar, no rules at all, no rules in forming the production rules. So this is about the types of grammars in the theory of computation. Types of grammars in the theory of computation. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.